745 Heavy is on the ILS, 25 left, slow, window 180.
25 Heavy, later runway 25 left, correct line number 2, following Company Heavy Airbus 38 mile farm.
Okay, number 2.
What's going on, guys? Flyby Simulations here, and welcome to the first video in what I hope turns into a long-standing series on this channel called Aircrafts Dissected. In this edition, we're specifically going to be focusing on the Boeing 737 series of aircraft modded by ZIBO in X-Plane 11. I hope to make this series one of the most comprehensive tutorials about the Boeing 737 for X-Plane 11, as I plan to delve into every switch, knob, and those pesky little alarms that are located all around the plane that often confuse new pilots attempting to learn how to operate this aircraft. That being said, I must mention that I am in no capacity a pilot in real life. I am a 19-year-old university student who has an unquenchable thirst for aviation, and the following video series is the culmination of hours of personal research, video tutorials on YouTube, and conversations with real-world pilots. I must also mention the things you learn in this series will also be applicable to the 737-700 and the 737-900 series made by the Ultimate team for X-Plane 11. Another important thing I must mention is that throughout the video, you'll constantly see either a red, yellow, or green rectangle in the top right-hand corner of the screen. These rectangles are there to showcase the importance of the switch or knob being talked about and will dynamically change as I continue my explanation from system to system. The green rectangle means that the system in question will be used on every flight. The yellow one represents rarely used systems, and the red rectangle, of course, means that the system in question is purely for emergency purposes and not used in standard operating procedures. I will be leaving timestamps in the description below for each of these green, yellow, and red indicators so as to honor your time and in order to make it easier for you to watch only certain sections of the video if you so please. Finally, it's also important to mention that though this aircraft is highly complex, I will do my best to explain how some of these systems work in addition to describing the functions of these switches and lights. However, since I want this YouTube video to be as concise as possible, I won't be able to cover every system in great depth, so I encourage you to leave your questions in the comments section and I will try to reply to as many of your questions as I can. One thing is certain though, by the end of this tutorial series, you will be comfortable, if not perfectly capable, to try to fly this aircraft yourself. I certainly do hope you guys enjoyed watching this video series as much as I enjoyed making it for you, so without further ado, let's jump into the flight deck. Alright, so welcome to the flight deck of the Boeing 737-800. So the first thing you guys should notice is that the aircraft is completely cold and dark, meaning that all of its systems are shut off with no lights or sounds that can be heard. This is the ideal state we want the aircraft to be in, and it should be this way when you load up the aircraft for the first time. So, in this video, we will be taking a look at the overhead panels of the flight deck and understand the different systems, switches, lights, and other features housed within it. You might have noticed that the overhead panel itself is divided into two distinct parts. One is towards the back of the flight deck, whereas the other one, with more switches and dials, is right above the pilots for ease of access. This is done for a reason, as most of the important systems, such as the aircraft's air conditioning systems, fuel, hydraulics, and primary electrical systems, are all housed within this part of the overhead panel. We differentiate these parts by calling this one the forward overhead panel and this one the aft overhead panel. In the interest of time, we will be covering only the forward overhead panel in this video, but fret not, as we will cover both the aft overhead panel and the central pedestal in the next video of the series. Now, if you're new to airliners, I would like to introduce a concept to you all called flows, wherein pilots navigate each of these really complicated looking panels in a top-down pattern from left to right. This allows them to memorize the correct position of the switches over time and preserve focus while navigating around the flight deck. We will be using a similar technique in this tutorial in order to become familiar with real-world aviation techniques. So, starting at the top left of the forward overhead panel, we have the flight control panel, which is responsible for housing all of the backup switches for the physical, movable flight surfaces on the aircraft. These include the flaps, slats, spoilers, ailerons, vertical stabilizers, and the rudder. These movable surfaces are controlled by hydraulic fluids present throughout the aircraft, and these two switch systems, A and B, are responsible for them. By default, these switches are set to the on position. You can view this by lifting up the cover for the switches and checking its position. The two switches also have low pressure lights underneath them to signify a failure or problem with either hydraulic system. Moving below, we have two flight spoiler switches, one for each wing inside which these systems are housed. Just like the hydraulic systems, both of these are covered and are set to the on position by default. Below this system is the yaw damper. Now, this is a very important system which, among other things, prevents an aerodynamic effect called the Dutch roll. To make things simple, the yaw damper actively uses the rudder to assist the aircraft in rolling or turning to either side, resulting in synchronized turning. If you have ever wondered how your coffee never spills over when the aircraft turns or banks to either side during flight, you have the yaw damper to thank. Now, up on top right of this panel, we have some standby hydraulic system lights that light up whenever they require the pilot's immediate attention. Underneath these are two switches pertaining to the alternate flaps system. The red switch on the left is the alternate flaps master switch, which is set to off by default. In an event that the normal flap settings don't work, the pilots would flip the cover and set the master to on, and then use the switch on the right to either extend or retract the flaps accordingly. Finally, underneath this are 4 lights that indicate problems with specific flight control subsystems within the aircraft. Below the flight control panel, you have these navigation and data source selector panels. As you might have noticed up above with the 2 flight control switches and the 2 spoiler switches, this aircraft, along with most other modern airliners flying today, are equipped with redundant systems that act as a backup in case the primary system fails. That's why there are 2 of each important system on the aircraft, and since navigation is extremely important to any aircraft, there are 2 different sources from which the pilots can obtain data about the navigational parameters of the flight at any point in time. The switches on this panel all pertain to the flight management system, which is responsible for calculating the aircraft's performance, trajectory, direction, and navigation. The first switch allows the pilots to choose the VHF navigation source from System 1 or System 2. These 2 switches achieve the same function but for the IRS or Inertial Reference System and the FMC or Flight Management Computer Systems. More on that later. Now, during normal operations, these switches are normally left in the middle position so that the aircraft can automatically choose the most appropriate system to draw information and data from. Underneath these 3 switches are 2 display-related switches which, in addition to just using the data for automatic calculations, also allow the pilots to choose whether the data displayed on their primary screens are from the primary or secondary backup systems. Normally, this panel is rarely touched by pilots during normal operations, except for when there is a known fault with a particular system that can't be fixed by local engineers or ground staff. In a scenario like this, pilots would manually change the data source using these switches in order to get accurate data throughout the flight. Now moving down, we have the fuel control panel. Now right off the bat, this gauge displays the fuel temperature. Thankfully, X-Plane 11 doesn't model fuel temperatures and their effects on aircraft performance, so you don't need to worry about that for normal point-to-point operations. On either side of the fuel temperature gauge are 2 lights for the engine and spar valves, 2 for each side of the aircraft. Now, for those of you who don't know, fuel in a modern airliner is normally stored in the wings and the fuselage of the aircraft. The wings are fueled first, and once they're full and more fuel is required to complete the journey, the central fuselage may also be fueled up. These 2 engine and spar valves, when illuminated, signify that fuel from the tanks are physically restricted from entering the engine, thereby preventing any explosions or other catastrophes from occurring when the aircraft is on the ground. Coming underneath, we have 2 fuel filter bypass lights. Normally, fuel from the tanks passes through an extensive filtration process before being injected into the engine for combustion and thrust. However, in the event that one of these filters experiences a fault or a failure, instead of cutting off fuel supply to the engine altogether, fuel will directly be fed into the engine without the filtration process being applied, and the light on the appropriate side will be illuminated. In the middle of these 2 lights is a fuel crossfeed light, under which is the fuel crossfeed valve. Now, to explain this, it's important to understand that the fuel systems on either side of the aircraft work independently of each other. This is to prevent an emergency from one side of the aircraft, such as a burst fuel tank, from affecting the other side. However, in the unlikely event that fuel is being drained unevenly from the 2 wing tanks, for example, the left tank is draining at a rate of 800 gallons per hour and the right one drains at 700 gallons per hour, this crossfeed valve may be turned by the pilot so that the fuel is shared between the 2 tanks. This can help prevent any problems with the weight and balance of the fuel, causing problems with the flying characteristics of the aircraft. The light in the middle shines brightly when the feed valves are physically moving to connect the 2 fuel lines and then becomes dim when the valves are in place and the crossfeed system is working as intended. Underneath this are the 6 individual fuel pumps that supply fuel from the fuel tanks to the engines. These 2 are for the central fuel tank located in the fuselage, and these 4 at the bottom are 2 individual pairs of pumps for the left and right wing tanks. It's also important to note that, for longer flights which require the central fuel pumps to be used, the aircraft will drain fuel from the center first before draining the fuel from the wings. When the fuel reserves in the central tanks have been depleted, the pilots will get a message on their recall indicators and they will manually shut the pumps off mid-flight. Coming to the next panel over here, we have the primary power metering and monitoring display. Now, dividing this display into two parts, on the left we have a DC ammeter and voltmeter to measure the supply of current and voltage using direct current, and on the right we have an AC ammeter and voltmeter measuring the supply of current and voltage using alternate current. Just above that is the CPS frequency indicator, which highlights the frequency with which electricity is being supplied or used by different systems in the aircraft. Underneath this display are three indicator lights which all illuminate when there is a problem with their associated systems. The first light illuminates when the onboard main battery is about to be discharged. The second light illuminates when there is a problem with the onboard TR unit, or the transformer rectifier unit, which is responsible for converting AC power to DC power. This third light illuminates when there is a fault with the electrical system as a whole. This button is a maintenance button, which is only used by ground crew and certified engineers when a particular part of the electrical system needs to be fixed. Coming down, this left knob allows the pilot to specifically see the power draw from various different selected systems in the aircraft using direct current. Notice how the numbers on the display change when I go from the power being supplied by the onboard battery to the various other electrical systems in the aircraft. The same is true for the right knob, but for monitoring AC power instead of DC power. Coming underneath, we have a black guarded cover under which is the primary battery switch. Shutting this cover down automatically switches the battery on, and this is normally the first button or switch to be manipulated by pilots when starting the aircraft from a cold and dark state. On the right, we have two switches controlling electrical supply to the passenger cabin. This left utility switch controls power being supplied to electrical heaters, cookers, or other electronic appliances that the flight attendants use to service the passengers. The switch on the right, labeled IFE/pass seat, stands for in-flight entertainment or passenger seat power, which enables passengers to use electricity to access the in-flight entertainment systems, as well as use power supplies to charge their own personal devices for airlines that support these. Moving below, we have the standby power and generator drive panel. Let's first cover this black guarded switch in the center and its associated light. This black guarded switch is the standby power switch, which is normally left to the auto position and is rarely manipulated by pilots during normal operations. The standby power system powers the most important electrical components that receive power through the standby bus bars or buses, as well as battery buses during partial or total electrical failure, so they're extremely important and better to not be messed with. The light on top illuminates when the standby power is manually switched off or if there's a fault with the system. On either side of this system are two red guarded covers, which are the engine electrical generator switches. During normal operation of the aircraft, the electricity is generated by the motion of the fan blades of the engines, sort of like a very fast windmill, which drives these generators. However, in the unlikely event that one of these generators experiences a problem, the pilots can manually flip the covers and disconnect the generators. Note that this is a permanent disconnection, and it physically prohibits the engine's turbines from acting as a power generation source for the aircraft. Only certified technicians and engineers are allowed to repair the system when the aircraft is safely on the ground, and even then the entire engine needs to be reopened and stripped apart for a new generator to be installed. Again, a system that doesn't need to be messed with for normal operations. Below this is the bus transfer and electrical source selector panel. However, we will come back to this panel after first looking at the APU panel, as it is important to first understand what the APU is and how it works before selecting it as an electrical source. So, coming to the APU panel, let's just first understand what it is. The APU, or the Auxiliary Power Unit, is a small jet engine situated in the tail of the plane, which works just like the electrical generators within the engines. It too, like a very fast mini windmill, generates electrical power for the aircraft while it is on the ground before the engines are running and when there is no GPU or ground power unit supplying power to the aircraft. Additionally, the APU also provides bleed air, which is a supply of very hot air that goes through many filtration processes to then be injected into the aircraft as breathable air for the crew and passengers, and also to be used to spin the engines to their idle speed during the engine start procedure. More on that later though. So, the first display we have here is this gauge with 4 indicator lights above it. The gauge itself is an EGT, or exhaust gas temperature gauge, which shows the temperature of the exhaust gas being expelled by the APU when it is running. The first light above the gauge is the maintenance light, which lights up when APU is in need of maintenance but the aircraft can still fly in this state. This is one of a very few number of important systems on the aircraft that doesn't need to be in perfect condition for the aircraft to operate safely. The second light is a low oil pressure light. This light always illuminates when the APU is being started, as the APU also requires fuel to stay running just like any other jet engine, and the oil pressure is low during the startup phase of the APU. This is completely normal, and the light should automatically extinguish when the APU is running and is stabilized and providing power to the aircraft. The light next to this signifies a fault with the APU as a whole, and unlike the maintenance light, requires the ground technicians and engineers to sort the problem out. The final light here is the overspeed light, which illuminates when the APU was either aborted during its startup sequence or if the APU has a general fault within it, as the turbine is spinning faster than specified safety standards. Finally, this is the APU master switch. The switch itself is spring-loaded, and to start the APU, simply flick the switch to the run position and release it. It will automatically switch back to the on position. You'll immediately notice the low pressure light come on as expected, and the EGT gauge will start rising to about 800 degrees, stabilize, and then return to a more reasonable temperature depending on weather conditions at the local airport. Alright, so now that we have a sound understanding of what the APU is and how it works, let's go back up to the bus transfer and electrical source selector panel and see what the different switches and lights mean. This first light here is the ground power availability light, which is illuminated when a GPU or ground power unit is connected to the aircraft and is supplying power. To use ground power, simply flick the switch down to the on position and you will see the aircraft come to life. Underneath this are the electrical bus and source selector switches. Starting from this black guarded switch, this is the bus transfer switch. Now, much like the standby power switch we explored earlier, this switch is also always left to the auto position for the aircraft to decide which source of electricity it wishes to use to power primary systems, and so that electrical power flows uninterruptedly throughout the aircraft at all times. These two pairs of lights on the side illuminate when either the transfer bus itself is off or if the transfer bus isn't receiving any power from a source. Underneath these lights on either side are two generator off lights for either side of the aircraft. These lights illuminate whenever there is an active electrical source that the aircraft can draw power from to power that side of the cockpit, which is normally the electrical generators within the engines themselves. Now, remember how I said that the left fuel system of the aircraft runs independently of the right? Well, the same is true here as well, as the left engine supplies power to the left side of the cockpit and the right engine supplies power to the right side of the cockpit. The reason? Redundancy and backup. Now, below each of these lights are engine generator source selector switches. When the pilots turn on the engines, they can then flick these switches to then draw power from the engine generators to power the aircraft. Similarly, this light in the center is the APU generator off bus light, which illuminates when the APU itself is available as a power source for the aircraft to use. It too has these two switches that can be flipped to power the left and right side of the aircraft respectively when the APU comes on. Okay guys, so I really hope I haven't bored you to death yet, but thankfully this next column is not as complicated as the first two and should be more fun and relatable for you guys. Starting with these two knobs at the top, they are both concerned with internal lighting in the flight deck. The first knob illuminates the circuit breaker panel behind the first officer's seat, and this second knob provides backlighting to all of the displays and switches of the overhead panel specifically. Coming down, this lavatory smoke light illuminates when smoke has been detected in any of the lavatories in the aircraft, when smokers feel the need to let loose or whatever their justification is before being fined or being imprisoned in some cases. Underneath this light are two equipment cooling switches which control the supply and exhaust of the cool air that is fed to all of the electrical systems in the aircraft to keep them cool even under heavy load. These switches are normally left to the normal mode unless an alternative mode is required for the specific operation of the flight. Underneath this is an open black cover which controls the emergency exit light strips that run along the cabin floors, as well as the emergency exit signs at the top of the doors on the aircraft. In a cold and dark state, these are normally set to the off position to conserve battery power. However, flipping the cover down automatically arms these lights in the unlikely event of an evacuation or an emergency. Underneath these are the seatbelt sign switch as well as the previously used no smoking sign switch, which has now been replaced by this new chimes switch. This is because smoking is banned on all domestic and international civil flights globally, and hence this switch is no longer needed but can be found on some old 737s still in service. The seatbelt sign switch is normally turned on after refueling has been completed at the departure airport and is turned to the auto position when the aircraft reaches its cruising altitude. The switch is never turned to its off position unless the pilots wish to bring the aircraft to its cold and dark state like you're seeing on screen right now. The chime switch simply sounds a chime in the cabin when the pilots wish to get the attention of flight attendants working in the galleys. Underneath these switches are two small switches to alert important personnel. The attend switch is another switch that chimes a sound in the cabin alerting the flight attendants, whereas the ground call switch alerts any ground handling personnel working with headsets plugged into the aircraft when the plane is safely parked on the ground. Finally, these two switches control the left and right windscreen wipers and basically work like they would in a car, with varying speed modes to be used depending on the severity of the weather. And that brings us to the final two panels on the forward overhead panel. So at the top of this column, we have four simple window heat switches which, when switched on, prevent icing from occurring on the four primary cockpit windows and fogging them up. This middle button is a test button that allows the pilots to test whether the on-off lights and the overheat warning lights are also working for the system. Underneath these are the probe heat switches, which electrically heat some of the sensitive equipment on the outside of the aircraft, such as pitot tubes, temperature sensors, as well as guided alpha vanes. The lights on either side of these switches denote problems with the outside components I just mentioned and are normally extinguished when the probe heat switches are turned on. If the heat switches are turned on and the lights still persist, you not only know you have a problem with the system, but exactly which system as well. Alright, moving underneath these switches is the anti-icing panel, where on the left side we have the wing anti-ice switch. Now, just like the APU, the engines also produce hot bleed air which can be introduced into the wing through the leading edge slats of the wings in order to prevent buildup of ice and maintain safe operation of the aircraft even in cold conditions. The light above illuminates brightly when the valve allowing the bleed air in is opening and becomes dim when it is locked open in a stable position. To the right of this switch are the two engine anti-ice switches, which are similar to the wing anti-ice switch but instead heat the two engines to prevent the buildup of ice. Additionally, instead of feeding the bleed air through the leading edge slats, the air is fed into the engines through the engine cowling, which is the front rim of the engine nacelle. The lights above each of these switches work identically to the light above the wing anti-ice switch. Alright, moving further below, we have the hydraulic pumps panel. Now, in this aircraft, there are two hydraulic systems, as mentioned before, A and B, that are powered by two different sources, namely the two engines as well as two electrical motors on either side of the aircraft. The four switches down here, therefore, allow the pilots to switch on the two hydraulic pumps powered by the two engines, as well as the other two hydraulic pumps powered by the electrical motors to fuel the hydraulic systems in this aircraft. The lights above simply display if there is low oil pressure in any of the pumps, and this is to be expected until the engines are turned on. Additionally, the pumps driven by the electrical motor also have an overheat light to make sure that the electrical system isn't malfunctioning while using the electrical motor to power the hydraulic system. Coming underneath, we have a series of lights to highlight which doors are open in the aircraft. Any door that is not armed and locked will have its corresponding light illuminated in this panel, as you can see here. Underneath this is the cockpit voice recorder, which is part of the black box system used to uncover pilot communications after an unfortunate crash or any other catastrophic incident with the aircraft. The voice recorder records the last 1.5 hours of voice communications between the two pilots before the moment of the crash. As of July 2020, these buttons here are not simulated in the ZIBO mod 737-800. Underneath the cockpit voice recorder are some analog instruments and buttons to measure pressurization systems within the aircraft. Now, it's important to understand that before every flight, after the doors are locked and sealed, the aircraft is pressurized internally in order to maintain a certain cabin pressure throughout the flight. This is based upon different factors such as the aircraft's planned cruising altitude as well as the altitude of the nearby terrain and local airport. However, the pressure is always kept below that of what you will find the atmospheric pressure to be below 10,000 feet. This is because at higher altitudes, the atmospheric pressure decreases, thereby disallowing human beings from inhaling oxygen present in the air, leading to hypoxia and permanent brain damage and even to death. Hence, this pressurization panel is extremely important, as it allows pilots to observe the outside air pressure represented by this longer needle compared to the pressure that is being maintained inside the aircraft represented by this smaller needle. A large enough imbalance between these two values, near this red 9 psi range, can cause structural damage to the aircraft. This altitude horn cutout switch on the right simply turns off an alarm that sounds when the pressurization system has a fault. Now, instead of moving on to the top of the next column like we've been doing so far, let's go to the second pressurization panel right here first, as a lot of the systems we just discussed in the previous panel are also applicable here. So at the top left of this panel are two lights. The first one indicates a problem with the auto pressurization system in the aircraft and is often accompanied by an alarm, which, as mentioned before, can be turned off by pressing this button over here. Right next to this is the off-schedule descent light, which comes on if the aircraft starts descending before its planned top of descent point, or if it descends faster than what was programmed in the flight management computer, with no interference by the pilots. Underneath these lights are the two knobs with individual displays to adjust certain pressurization parameters within the aircraft. The first knob pertains to the flight altitude panel, where the pilots program the planned cruising altitude for the flight in order to help the aircraft plan the differential pressure between the outside and the cabin. Underneath this knob is the landing altitude knob, where pilots will set the altitude of their arrival airport, which also assists the pressurization systems in performing their tasks. Moving to the right, we have this analog gauge that allows the pilots to monitor the position of the physical valve that moves to let more or less air into the cabin to manage differential pressure. This switch in the middle allows the pilots to manually open or close the pressurization valve outside the aircraft to manipulate differential pressure manually. Below, this knob allows the pilots to switch from the automatic pressure system to the alternate or manual pressure systems. This will also consequently illuminate their corresponding lights above these switches. However, it's worth mentioning that if you're having to switch to these systems, you're having a really bad day, as pilots would normally never need to use these systems on normal point-to-point flights. And that, ladies and gentlemen, brings us to the final column of the forward overhead panel, which mainly deals with the air temperature control as well as the air conditioning systems in the aircraft. So, starting here, we have an analog gauge which displays the current temperature in different regions of the aircraft. Using this knob to the side allows the pilots to manually monitor the air temperature in different zones of the aircraft, such as the control cabin or the flight deck, as well as the different passenger cabins. Notice how the needle on the gauge jumps up and down as the source selector is changed. Underneath these two is a trim air switch. Now, to understand the trim air system, you need to understand a basic overview of the air conditioning system inside the Boeing 737-800. Bleed air is first produced at a source, which in this case is normally the engines during flight. Now, keep in mind that bleed air is extremely hot and hence needs to be cooled before entering the cabin, so it enters a system called a PAC, or a pneumatic air cycle kit, which cools this extremely hot bleed air to near freezing temperatures. From here, trim air is used to fine-tune the temperature of this air now coming from the PAC systems before entering the cabin to be used as breathable air. Hence, the trim air system is very important to control the temperature of the air entering the cabin for both the passengers as well as the flight crew. Underneath the trim air switch are 3 zone temperature lights, followed by 3 zone air temperature control knobs to control the temperature in the control cabin or flight deck, the forward passenger cabin or business class, and the aft passenger cabin, normally economy class. The zone lights will come on if the air temperature is becoming too hot or too cold, which normally indicates a problem with either the PAC system or the trim air system. Coming underneath these knobs, we have the air conditioning panel of the aircraft. Right off the bat, we see 3 lights, which we will come back to in a second. Below these lights, we have the left and right recirculation fans. Now, the purpose of these fans is to take the air already present in the cabin and feed it back into the system to be reintroduced into the cabin. This reduces the need for more bleed air to be produced by the engines, thereby reducing the workload of the air conditioning units in the aircraft. Below these switches, in the middle, we have another analog gauge that displays the duct pressure of the 2 feed lines in the recirculation fan systems that carry the air around the aircraft. This little switch is a simple overheat test switch to make sure that the overheat light indicators below are working. Come underneath, we have 3 important switches pertaining to the PAC systems in the aircraft. These 2 switches allow the pilots to switch between turning the PACs off to their automatic mode or to high mode, wherein the PACs will work faster to cool bleed air that is coming from the engines. It's important to note, however, that the PAC systems are normally left to the auto position so as to let the automatic air conditioning systems in the aircraft to decide the optimal usage for the PAC systems. In the middle, we have an isolation valve switch, which is extremely similar to the crossfeed valve on the fuel control panel we explored before. The isolation valve's function is to link the 2 bleed air ducts that would otherwise work individually on either side of the aircraft in case there's an issue with one of the PAC systems and the other PAC needs to handle more bleed air now coming from both engines. Coming underneath, we have a pair of 3 warning lights that illuminate when a problem occurs with their associated systems. The first light on either side illuminates when there is a problem with either of the pack systems. The second wing body overheat light illuminates when there is a leak in the bleed air ducts passing through the wings and the fuselage of the aircraft. We just tested this using the switch up above. Finally, the last light down here is a bleed trip off light, which illuminates when the bleed air being supplied to the pack is too hot, thereby leading to an increase in heat in the pack system, causing it to shut off. When pilots identify this problem, they can either choose to turn off the pack systems and allow them to cool down, or if it's only one pack that's malfunctioning, they can turn the isolation valve to on and turn the other pack system to high speed to take over the responsibility of the malfunctioned pack system. This trip reset light is there to reset the malfunctioning pack system once it's done cooling down to resume normal operations. Finally, underneath here, we have 3 air source selector switches to acquire bleed air from. On either side are the engine bleed switches, which when turned on take bleed air from the engines to then use for air conditioning. In the center is an APU bleed air switch, which allows the packs to use bleed air from the APU when on the ground to cool the aircraft before engines start and to also aid in providing the air for the engine start procedure. When the engine bleed switches and the APU bleed switches are on at the same time, you get this dual bleed light, alerting the pilots that the pack systems are receiving bleed air from 2 different sources. As for the ram door full open lights, they come on only on the ground. This is because the ram door is a small physical valve on the outside of the aircraft that lets cool air into the pack system to allow it to cool the bleed air produced by the engines. During flight, having the ram door open partially will suffice, as the cool outside air is entering the ram door at a high speed. On the ground, however, when the aircraft is stationary, the entire ram door needs to be opened to use the cool outside air for the packs. And that, ladies and gentlemen, covers the majority of the forward overhead panel. Now all we have left is this little strip of switches below, which all pertain to the external lights of the aircraft and some engine related switches. Coming all the way to the left, we have the retractable landing light switches, which come down from their stowed position inside the belly of the aircraft and shine forwards. These 2 lights on the side are the fixed landing lights, which serve the same purpose as the retractable ones but are located on the leading edge of the wings and don't need to be stowed. These 2 switches are the runway turn-off switches, which shine a bright straight ray of light at an angle from the front, allowing pilots to see where they are about to turn while taxiing at night, as well as poor visibility conditions such as fog. This light here is the taxi light, which simply illuminates a bright straight light located on the nose wheel of the aircraft to allow pilots to see where they're going while taxiing on the ground. Now we've already covered the APU, so let's just keep on going and we then come to the engine start switches, 1 for each engine of course. Flicking these switches to the ground position begins the engine start procedure, which involves taking bleed air from the APU to spin the engines to their idle speed before injecting fuel into them. The continuous and flight modes on this knob are used when flying through severe precipitation such as rain or snow, as it makes sure that the engine igniters are constantly keeping the engines running regardless of the large amounts of water and moisture entering the engines during such harsh weather conditions. In the center, we have an engine igniter switch, which pilots use to decide which engine igniters the aircraft should use to start both engines. Pilots normally never put this switch to both, and usually choose one igniter for the first flight leg and the other igniter for the return leg in order to use both igniters equally throughout the lifespan of the aircraft. Moving further right, we have some more external light switches for the aircraft. The logo light illuminates the logo of the airline, or the tail of the aircraft of course. The position light has 3 modes: off, steady, and strobe and steady. When switched to steady, the position lights at the tip of the wings light up as green on the right wing and red on the left wing. This serves 2 purposes. Number 1 is to alert ground crew that pilots or other flight personnel are currently working in the aircraft, and number 2 is to allow their planes taxiing around the airport to know whether the aircraft is coming towards them or moving away from them. Flicking this same switch to the strobe and steady position illuminates the ends of the wing in a strobe pattern, so as to alert other pilots on the ground as well as in the air that an aircraft is in their line of sight. Moving over, this switch is the anti-collision light switch, which is a red strobe light on the top and bottom of the aircraft fuselage. This light is turned on before engine start to alert ground crew that the engines are about to be started and they should disconnect any ground equipment still attached to the aircraft and move away from the plane. Finally, these 2 lights illuminate the underside of the wing and the wheel well compartment inside the landing gear of the aircraft. Finally, this last switch helps control the lighting of the standby compass instrument on the top of the glare shield, allowing pilots to switch between dim and bright modes. Quite old school, I like it. And that, ladies and gentlemen, brings us to the end of the exploration of the forward overhead panel on the Boeing 737-800. If you made it this far, congratulations! You now have a sound understanding about every major system on this aircraft and are now aware of the functionality of practically every knob, switch, alarm, and light above the pilots in the flight deck. Now, I must also mention that all of the documentation and websites I used to research for this video are linked down below in the description, including a written text version of this entire video as well, if you prefer to read those and understand more about this aircraft. That being said, the next video in the series will focus on the aft overhead panel and the central pedestal, which houses all of the navigation and radio equipment that pilots use to communicate with air traffic control and should be coming out very, very soon. If you guys enjoyed the video, make sure to fly by the comment section and let me know if there's any questions you'd like me to answer for you. Make sure to perform a full stop landing at the like button and the subscribe button if you enjoyed the content, and press the bell icon for future updates from this channel. And as usual, thanks for flying by.